So it's a pleasure to present my work today. And so I will talk about the AMOC, I will talk about ice sheets, and obviously about tipping elements. But so all the things I will show you today is basically a synthesis, but also, some thoughts on my work that I've done for the PhD thesis. That's, as Sebastian said, has very recently been defended successfully. So that is done, but let's go. So climate tipping points, I don't know to which extent I should introduce them, but basically, so we know we have different climate systems in the biosphere, atmosphere, ocean, in the cryosphere that are thought to have some critical behavior above some temperature. And we now try more and more to try to narrow down a bit what these tipping points could be. Can go from quite low to quite high, and especially we see that some of them are at temperature possibly that have already been crossed. If you look basically just the climate warming of today, you see that I never really know which number I should say from this curve, but like up to 1.6, something around 1.4. So the polar ice sheets and the coral reefs may already be just above that, or like above their tipping points. Now that's one aspect of the problem, obviously, that we try to narrow down these tipping points, but we also try to narrow down the tipping timescales. There's a huge variety of probable tipping timescales, from some years to some centuries to some millennia when it comes to polar ice sheets. Um, and obviously, when you think about the fact that these elements could be also coupled, that brings one more layer of complexity. And what I've been working on mostly is the interaction of tipping elements. And so maybe just to illustrate that first, we have the AMOC, so the Atlantic Ocean Circulation, that's a lot of you must know about, that we know is sensitive to freshwater input. And then we have polar ice sheets. We know Greenland is mostly sensitive to atmospheric warming, that West Antarctica is mostly sensitive to ocean warming. But then it sets the ground for possibly a melting of Greenland or a tipping of Greenland that could cascade into a cascading tipping where the AMOC would also collapse. Now we know that the AMOC, when it weakens or when it tips, implies some climate change, including surface air temperature anomaly that could actually stabilize the Greenland ice sheet because of this cooling in the northern hemisphere. Now there's also warming in the southern hemisphere, in the air temperature, but also in the ocean temperature that could trigger the melting of West Antarctica. Now, the coupling of West Antarctica to the AMOC is quite uncertain, but obviously I will talk about extensively about it in the following minutes. So that's just part of the problem, obviously, because then we know that sea level rise is mutually destabilizing between ice sheets. We know that a collapse of the AMOC again could do precipitation anomalies on the ITCZ and stuff like that, that could obviously impact the Amazon rainforest, the monsoon system. And you can imagine that the collapse of West Antarctica could only be bad for East Antarctica. So it's just, and I mean, here it's a subset of tipping elements and a subset of interaction. So this is actually a very complicated problem we face. You can study tipping elements one by one, try to understand their dynamics and stuff, but for the future, obviously, this kind of behavior will totally change the trajectory of the climate, right? And there was an effort recently, I mean, not so recently anymore, but that was updated recently to try to quantify a bit these interactions, and especially to know which ones are stabilizing, destabilizing. And what we sort of concluded is that among the ones we have considered, 15 would be destabilizing, 4 would be stabilizing, and 1 totally unclear. And this is the update of this report, because before, the West Antarctica ice sheet to AMOC interaction was in unclear, and it has been sort of upgraded to a stabilizing with very low confidence. And the reason why is, not only what I will present you, but that was part of the reason why this change has been made. And so what we care about today is really the AMOC and the ice sheets. So before going into the topic, maybe a brief reminder of like what are the positive feedback loops that we find in this system. So not in terms of interactions, but really in terms of for each tipping element. So for the Greenland ice sheet, we have an ice sheet that has basically the property of being on land, right, above the sea level, and that is quite high, and that makes it sensitive to a feedback that has to do with the fact that temperature is higher close to the ground. And so if the ice sheet is high enough, it can be higher than what we call the equilibrium line, above which ice forms and under which ice melts. And so if enough of the ice sheet is above that, ice formation and ice melting is compensated and it is at equilibrium. Now, if the ice sheet melts, it's less high, right? And less of the ice sheet is above this equilibrium line, which means that the balance is broken and it will collapse to a no ice situation, what I call the melt elevation feedback, but you've maybe heard that under height SMB feedback or things like that. But that refers in general to at least more or less the same process. But so that's for the Greenland ice sheet. For the AMOC, so maybe let's show the AMOC very fast. So some hot and dense water that goes to the north and sinks and goes back to the southern hemisphere from the depth to be upwells. And so if you simplify this circulation, you can look at it from the side. And so what maintain this, there are a lot of things that maintain this circulation turning, but the water evaporates at the equator where it's hotter. And so the water that goes to the north is rather salty and so rather heavy. And that allows it to sink and then come back to the south. But now, if you had less salty waters in the northern hemisphere, for example, because an ice sheet collapses, the sinking of water in this hemisphere will be less strong. So the AMOC will be less strong, and so less salt will be exported to the north, and that's what we call the salt advection feedback. And this is, at least as far as I can tell, the main understanding we have today of the AMOC collapse. It's really this process. And so now, at last, we have the West Antarctic Ice Sheet. So the western parts of the Antarctic ice sheet, which, unlike Greenland's, is mostly grounded under sea level. And that makes it a physically different object that we call a marine ice sheet. Again, you can conceptualize it to look at it from a land-based ice sheet here, but that then extends into an ice shelf that floats on the water. And we know, or we think, that it can only be stable if the grounding line, so this point here, is on a slope that goes in this direction. If it reaches this zone, it becomes unstable. Now, if you would melt the ice sheet for whatever reason and push this grounding line beyond this topographic maximum, it would become unstable and transition to the next stable point, which in this case would be around there. And that's what we call the marine ice sheet instability. So that's all the feedback loops I care about here. And so the first conceptual approach that I've done was really the idea of let's represent them, these feedback loops, let's couple them together and then warm this up and just see what happens. And so that was the object of this first publication in Geophysical Research Letters that you have maybe seen around. But so what we did was we take a box model for the AMOC that represents this salt advection feedback. Then in the north, we put a Greenland ice sheet. And in the south, we put a marine ice sheet. And so each of these models representing the main feedback that drives these components to tipping. And then we warm this up. What classically happens is that the Greenland ice sheet collapses first, puts this fresh water in the northern box, which weakens or makes the AMOC collapse. And that brings warmer southern box in the Atlantic Ocean, which can trigger the collapse of the marine ice sheets, which itself will put fresh water in the southern box. And so what's important to note in this box model is that you expect that this fresh water from West Antarctica will stabilize the AMOC. And it's quite trivial, actually. And I think maybe you can stop me if I'm wrong, but that any box model shows this behavior because the AMOC strength is parameterized directly as the density difference between the north and the south. So if you put fresh water in the southern box, it's totally trivial that the AMOC strength will increase. But, nonetheless, when will you find an AMOC tipping or stabilization? The two big parameters here will be how much the climate warms, so this because it triggers the chain of events, and what is the West Antarctica sensitivity to this warming in the Southern Ocean. That will dictate how fast it tips, if it tips, and all that. So let's see. We will warm the climate for 100 years on one side and for 300 years on the other. And we will vary by how much we warm it in the x-axis and the sensitivity of West Antarctica to ocean warming on the left axis. And then we find two different regions. It's worth noting that for any of these parameters, the Greenland collapses and triggers an AMOC collapse. Okay, but we find that in yellow you have indeed this cascading phenomenon, but in blue, when you add West Antarctica, you have actually the AMOC that does not collapse. So that's what we would call here the AMOC stabilization driven by the West Antarctic ice sheet. And if you look at where it happens, you see that it's on a range of about a half degree that this effect is relevant. And to put it maybe in perspective, you can look at the predictions for temperature for the next 100 or 300 years. And then what you see is that for 100 years, basically this range was up there. So at very high warming, that would probably not really be reached in the next 100 years, or even in the worst case. But in 300 years, it's right in the middle of these high emission scenarios, right? So it suggests that it could be relevant in this case. But basically, the point is that the AMOC stabilization may be relevant in the future, at least if you believe this box model, obviously. And what's important here is obviously the warming, and I don't show that here, but I've done also like hosing experiments and stuff like that, and you see that the crucial parameters here are how much time the West Antarctic ice sheet takes to collapse, and what is the delay of initiation between the Greenland ice sheet tipping and the West Antarctic ice sheet tipping. Right, so that concludes the first conceptual study. And now, after that, we wanted basically to sort of validate that in a better box model, to have a better idea of like the robustness of this effect, but also investigate the rate and noise-induced effects that we know are present in tipping phenomena, and especially for timescale that's separated between the AMOC and the ice sheet. And that was another publication in Earth Systems Dynamics. And so what we did there is we took, as I say, a better box model for the AMOC. So we have 5 boxes, so 2 more, but especially we have like a dynamical representation of the Picnock line depth, which makes it more realistic. And overall, I mean, I would say the box model is probably just better parameterized. But we totally gave up on trying to having dynamical representation of ice sheets, for the simple fact that you don't really need to have a dynamical ice sheet to prove this point, right? You just need to put fresh water and see what happens. But so we will, and again, just to make my point, in this box model, you expect the stabilization to occur when West Antarctica gives fresh water, because again, the AMOC strength is the meridional density gradient. But so now we parameterize ice sheet as a parabola that has this shape, and systematically we put the ice or the freshwater content of the respective ice sheet. And for example, if we put freshwater with this shape from Greenland, so in the north, we find an AMOC collapse. But now if we add another freshwater input in the south from West Antarctica, we find an AMOC stabilization, so no collapse. And so these freshwater trajectories are parameterized by the delay of initiation and by the duration of the West Antarctic tipping, always keeping the Greenland ice sheet forcing trajectory constant, so 1,000 years to deliver all its freshwater. And so we can look in this parameter space, basically, which are the West Antarctica trajectory that will lead to a stabilization. And this region is this one, what I call here the no-tipping region. And because it's a box model and it has a well-understandable bifurcation structure, we can also try to understand why the stabilization occurs. And for this, we look at the bifurcation diagram that will have a shape that is probably familiar to most of you. So we have this upper stable branch, lower unstable branch, actually an alternative steady state that's a collapsed AMOC, and then a tipping point that is a southern node bifurcation. So that's obviously the AMOC states when you and the equilibrium AMOC states when you increase the Greenland's freshwater flux. Now, if you increase the southern freshwater flux, so you put it at a higher constant value, you can redraw this bifurcation diagram and you find this. So basically, the tipping points of the AMOC occurs at higher values of the Greenland's meltwater flux. Now you increase it a bit again, you find this. So you get the points. The tipping points is just further to reach when I put freshwater in the south. And there, I'm not going to go too much in details, but this sort of linear translation of the tipping points when the freshwater flux goes up allows us to do some mathematics, actually, and to find which trajectories of West Antarctica will lead the AMOC to never leave, basically never cross the tipping point. So what I can call a no overshoot region. So that's where the stabilization should occur if this is bifurcation-induced phenomena. But the no tipping region I showed you before, so the one found experimentally is this one. So specifically, you find some configurations in which tipping occurs without overshoot of the tipping points, and another where overshoot occurs without tipping, which shouldn't occur for a bifurcation-induced phenomenon. Obviously, the first suspect here is rate-induced phenomena. And to sort of validate this hypothesis, we can just decrease the rates artificially and see if those two regions match. And what we see is that doing that, so in the lighter blue curves, you see that progressively the match becomes better when you decrease the rate of forcing artificially. And so that's at least a sort of first approach to how the rates of forcing, and especially the timescale separation between ice sheets and the AMOC can influence the stabilization phenomenon. Now, the other half of the study had to do with noise-induced phenomena, but I'm not going to go into that because, it's big plots with like a lot of setup and stuff like that. I think it's just too much. But I did a little animation. And like if there is like, epileptic people in the room, maybe close your eyes for 10 seconds. So we can compute the evolution of the AMOC tipping probability in time when we add noise, to find noise-induced transitions. And here, that's what I show. It's the same parameter space. I didn't put axes or numbers or anything, but the point is that it converges in time to a region that looks like what we saw just before, where basically the AMOC tipping probability is decreased when West Antarctica gives fresh water. But again, from bifurcation-induced tipping, there is a shift between the stabilization region and where it should be when you understand the bifurcation diagram of the model. And furthermore, we could also show that it was not rate-induced effects this time. Again, via the same method, you just decrease the rate and you see if the match occurs or not. So this shift now here is a rate-induced effect. So basically, mean, obviously it is a box model, right? But we could say that the AMOC stabilization is at least consistent with one of the box model that is a bit better, but also, and more importantly, that it is much more complicated than just a bifurcation-induced phenomenon. So basically, hysteresis experiments and stuff like that, we cannot really expect too much that they will tell us where it could occur or not. So now, these are the two conceptual approaches I have had. Obviously, it would be very much incomplete if at some points you don't try to investigate that in an actual climate model. And that is the object of this last study I present, which is simply evaluate all that in an actual climate model. And when I say all that, it's mostly just seeing if you find the stabilization. I'm not going to talk about noise or rate or stuff like that too much. And so that's something you can find actually on arXiv. I hoped that it would be published by today, so I could give you a QR code or something like that. But you should find it in Science Advances within 1 week or two. The title has changed a bit, but you will recognize me probably. And so the idea here was, let's use Climber X, which, if you don't know, is an intermediate complexity climate model. And we will do basically the same experiment. So we select the Greenland region where we will put fresh water and the West Antarctica region where we also put fresh water. And we do it in the same way as what I showed before. So we parameterize these fluxes with their duration and with the delay between their initiation. And we just try to find which of these forcing will lead to tipping or stabilization. Also, systematically, again, we put exactly the volume of each ice sheets into the ocean, and may I say, without compensation, which I think makes most sense when you try to simulate an ice sheet giving fresh water. And so, now, what do we see? I show here one trajectory of Greenland that's basically tips in 3,500 years. And you see a collapse of the AMOC. Now, maybe some of you will, be a bit surprised because the collapse of the AMOC here happens at quite a low forcing, right? I mean, the maximum of the Greenland ice sheet forcing here is like 0.04 or something. It's a drop. But the point here is not to show that Greenland can collapse the AMOC, obviously, is to put West Antarctica flux and see what occurs. And so let's do that. We've done a brute force approach. Let's just add a lot of different trajectories from West Antarctica and see what occurs, basically. And so they are still defined, in this same parameter space I showed before. For the moment, it's gray, but there will be colors soon. And to put colors, we will put a metric here, which is the difference in weak AMOC duration. So basically, when it's negative, it's stabilization. When it's positive, it's worse, basically. So the AMOC is weak for more time. And so let's see. First, we see some trajectories of West Antarctica that leads to a recovery of the AMOC. So the AMOC recovers in any case, but in these cases, it triggers like something like 1,000 years before or something like that. So this resonates a lot with previous studies, actually, because, and I will talk about it again at the end a bit, but people have found before, I think, so it was 2008, I think about the study of Weaver et al., that in the paleoclimate events, it is an hypothesis that the collapse in Antarctica might have brought the AMOC from shutdown to a stable active state. So that resonates with this. Now we have another set of trajectories where basically West Antarctica makes it a bit worse, either because the AMOC collapses earlier or because the AMOC recovers later. Okay, so it spends more time in a weak state. Now we have another set of trajectories where it makes the tipping later, basically. So it's, again, I mean, that's something that was observed in previous literature in other models. They could delay the AMOC collapse. But then, as you imagine, I was most happy to see the other trajectories, the green ones, where you see that the West Antarctic flux happening here, around there, can actually totally prevent an AMOC collapse. Now, totally prevent, obviously, you will tell me it still decreases by like more than 50%. Yes, but it prevents the collapse in a way that the weak AMOC state duration is decreased by up to, like, I think it was 2,300 years or something like that. So that's already one thing. Now, why does it occur? To know why it will occur, let's look at this specific situation where, again, Greenland is here in black. We add the West Antarctic flux in green. And so here in black, you see the only Greenland trajectories, and here in green, both ice sheets at the same time. And so the mechanism you would expect if you trust box models is the trivial one, in which you impact the density difference, so the AMOC gains strength. And basically this is, I mean, not exactly, but this is close to what people call the bipolar seesaw, which is an important mechanism in this context, especially in paleoclimate. And basically it means that if you decrease deep water formation on one pole, you increase it on the other, and vice versa. So we talk about North Atlantic deep water in the north and Antarctic bottom water in the south. But there is a problem. The problem is, I mean, the first big problem is that we see that West Antarctica doesn't at all strengthen the AMOC. It weakens the AMOC in the first time. So we have to find a solution to that. And also, we know more or less that the bipolar seesaw does not act on the millennial timescale. It's more something you will find after a few decades and for a few decades, or like a century or something like that. So we have to find another mechanistic explanation that can take account of all that. And that's what we try to do. So basically what happens is West Antarctica gives fresh water. This fresh water, because of the AMOC, will go to the North Atlantic, and that will lead to an accelerated AMOC weakening. And that's consistent with what we knew about this situation, right? Fresh water goes to the North Atlantic, so the AMOC weakens. And you see that here in blue. Now, at the end of this phase, you see that the Greenland ice sheet also begins to give a non-negligible freshwater flux, if I may say. And so one plus the other, basically, it will lead to an early collapse of this northern circulation, basically the convection around Greenland, because now there is more fresh water there than if West Antarctica was not there. So it's an early collapse, but not to a shutdown. Just, I mean, it looks a bit like a micro tipping, if you could call it this way, but to this level. And then what we see is that there is still convection occurring under this region. So, under the Labrador Sea and all these regions where you would usually see the convection, there is still a weak convection that allows for the AMOC to remain at this level. And basically what saves the AMOC now, the way in which West Antarctica has saved the AMOC is because the death of this circulation around Greenland implies that most of the fresh water that Greenland gives will stay around Greenland and not interact too much with the convection region that is weak but still existing more in the south. So now still some of this fresh water will go there and be exported to the south, right? And so, all of this is backed up by a freshwater balance, but what you see at the end is that you have an increasing density in the north, which favors convection there. And you also have a decreasing density in the south, which favors the increase of the meridional density gradient, which we know is correlated to some extent with the AMOC strength. And that leads to the stabilization and eventual recovery of the Atlantic circulation. Right. So now, if you believe in tipping points, and if you believe in the review we had from Armstrong-Mackay, obviously we have to use something, right? You see that the ice sheets minimal and upper tipping threshold were between 1 and 3 degrees of global warming, which would mean that, within the next century, high emission scenarios will lead to the tipping of the polar ice sheets. And so if we go from this understanding, in this parameter space we see, it means that they will collapse with less than a century of delay, basically, which puts us in this region of the parameter space in which the only possibilities are either an AMOC stabilization or a worse AMOC tipping, depending on the time it takes for West Antarctica to collapse. So the point now is that first we find the AMOC stabilization in a climate model of intermediate complexity, and that it seems to be consistent with high emission scenarios, which the previous conceptual studies also seemed to point out. And that will lead me to a three-step conclusion. First, trying to bind a bit the conceptual and the model approaches, in the sense that they agree on the existence, let's say, of this effect, at least the models I used, obviously. But they strongly disagree on the mechanisms that bring this stabilization. On one hand, we have the box models where it only occurs because of the definition, basically, of the AMOC strength. And then we have Climber X, where the AMOC stabilizes because it weakens to a state that is more resilient to the Greenland meltwater. So you could nearly argue that it was a bit chance to find it after the conceptual studies. So that's one part. Now, another thing, so I call that unpopular opinion. It's not really unpopular. I just like the phrasing of it, but weak interactions are important. And the reason for that is that nonlinearity or chaos or that kind of complexity does not care so much about what is strong or weak. Cares about it, obviously, but we are well placed in the tipping community to know that little changes bring, little triggers can bring big changes. And to see it in my experiments here, you can look here on the left how the Greenland meltwater impacts the AMOC and how the West Antarctic meltwater impacts the AMOC. Also the difference of magnitude of these forcings, and you would judge that, and quite fairly, that the West Antarctic impact is really weak. I mean, it's still substantial, but it's at least much weaker than what the Greenland does. But now you put it together, and you see that the proportion of both of these impacts is not additional, right? I mean, this little change that West Antarctica did on the AMOC now has a huge impact when you put it in the network of interacting tipping elements. And I would suggest that, when you study interacting tipping elements, obviously the strong interactions will be the priority, but the weak one can totally change the trajectory of the climate. So, should not be forgotten, at least. And now, for last, a bit of outlook, because I don't know if there are some, climatologists in here, but what struck me was this story of the Meltwater Pulse 1A, which, for the people who don't know that, is something that happens about 12,000 years ago, where you would see that the sea level would rise by about 20 meters in less than 500 years, which is a totally ridiculous amount of sea level rise for this time. And that is considered a sort of precursor of the last deglaciation, in which the temperature would rise, which would mean that the northern hemisphere would melt, but at the same time the AMOC would strengthen. And that is not very compatible. I mean, in principle, when fresh water is released in the north, you expect at least that the AMOC doesn't strengthen, but also that it weakens. And in fact, in my experiment here, what I see, maybe with different magnitudes and stuff like that, but at least in terms of timing, is that you have this meltwater pulse when West Antarctica delivers fresh water, and then you have an AMOC recovering while the Greenland ice sheet's meltwater flux is actually increasing, which is a similar signal. And as I said maybe earlier, the meltwater pulse was already in the literature considered to possibly have been caused by release of fresh water in the southern hemisphere. So I find that interesting. I would be happy to talk about it, maybe with you people later. But yeah, that brings me to the end. So thank you so much. And I will gladly take any juicy questions.
Thanks very much. Very cool. And 3 papers in one story. So I'm sure there are questions. Oh, there's a very long comment in the chat.
Is there? Yeah.
Is there a question in there?
I don't see questions.
Maybe not. Okay. Any questions?
Tick, tick, tick.
Then please.
I mean, I see some people at least. I mean, the first I see is Jan.
Oh, yeah, indeed.
I think Henry was before me. If he wants to go.
Okay. Yes.
Sure. Hi, thanks for the great talk, Sacha.
Thank you.
I had a question about the response of the AMOC to Antarctic melt. So what I'm trying to wrap my head around is that there's this other community that takes like the best GCMs we have. So, you know, kind of CNET 6 class models, and then does hosing experiments either with like Greenland melt or Antarctic melt. And they usually do those one at a time. And like, it's a pretty abrupt kind of step function forcing. And usually they see that there's very little effect of Antarctic melt on the AMOC. And then they also do experiments where they add the two at the same time. And my interpretation is that it's actually pretty linear. So you can just add the response to the circulation from the Greenland melt and the Antarctic melt. And so I was confused about this until your last few slides, where now my interpretation is that basically all of those experiments are in this one regime where they don't really interact very much. And so you can kind of just add the responses together. Whereas what you're highlighting is this regime where if the WAIS melt kind of happens early enough relative to the Greenland ice sheet, that then they do interact a lot. Does that match your interpretation?
So, I mean, maybe to put that a bit in perspective, because I'm not totally sure of which study you really refer to, because obviously there are a lot of them. But if you talk about the big models, like GCMs and stuff like that, you probably don't think about studies that look at the AMOC response on like 2000 years or stuff like that, right? And you could probably judge for the first decades, if I zoom on this little region there, that's maybe the response was actually additive, because you see, well, not even actually. No, not even. So what I would say is here, the experiments were analyzing the AMOC response on the billionial timescale, obviously. And there, that's definitely not what I observed. But I mean, I've seen also GCM experiments where you would have both fluxes at the same time on maybe 50, 100 years or stuff like that. That's obviously not very informative on the actual influence that it will have on the long term, because on the decadal timescale, I mean, you basically what I see in Climber X on the decadal timescale is mostly what you would consider as noise, right? I don't know if it answers to the question, but that would be my take on that, at least at first.
Yeah, that makes sense. So all these experiments I'm thinking of are 50 or 100 years.
Yeah, exactly.
Thanks a lot. And then Jan, you were next.
Yeah, hi Sacha. Thank you for the talk. It was really nice to see all of these pieces coming nicely together. I'm wondering, because at some point we talked about how to put the fresh water from Antarctica into your ocean model. And I see, well, you have this brown mask, I think, on one of your figure. And I see that, for instance, you know, there is no West Antarctic Ice Sheet meltwater that goes anywhere beyond what's in the vicinity, really, of the WAIS. Although, I mean, I think from, you know, people doing some Lagrangian stuff, trying to track a bit where the meltwater goes, it tends to, I think, spread quite a lot around Antarctica. And I mean, not to say that you have to use it, but did you try to change the mask and see how it would affect the result, just to know how robust it is?
So I didn't try to change the mask. The idea here was really just to put fresh water at the border of West Antarctica and just let it propagate from, whatever the Southern Ocean would decide it does, right? And also it's a surface freshwater flux. It's not applied in the depth, which was the object of a spicy question I had for my PhD defense, actually. But in this case, yes, I mean, that's what we tried. We didn't try something else. But yeah, I mean, at the end, letting the Southern Ocean do what it wants, I guess, is the first wise step to do.
Yeah, the thing is, I mean, you won't resolve, I think at the resolutions you have, you won't resolve, finally what's happening along the coast of Antarctica.
No, sure
which,
not.
I mean, there's the ACC, but then there is the kind of opposite circulation more
sure.
towards the interior.
Yeah.
But yeah,
at the end, like when you use a model of a certain complexity, you will always have other people to tell you that the higher one will resolve the thing that you are looking for. That was the case with Box model.
And I think, I mean, the solution is not necessarily to go more complex, but just try the permutation and, see if it affects the
Makes sense. Could be done, I guess.
Yeah.
Would be interesting.
And just maybe a very small thing. I mean, let's say the outlook. I mean, is it something you want to address at some point with the same tools, or I mean,
with the same tool, I don't know if it's gonna be possible, but I guess it would be. I wanted to talk about it actually with Marissa when she comes this week to Utrecht. But yeah, I mean, for the moment, it's really just a thought I have, and I will think about it a bit more.
Okay, cool. Thank you.
Thank you.
And then Jonathan is next.
Yeah. Hi, Sacha. Thank you for this very nice talk. I have a kind of question similar to Jan asking you about model complexity, so I apologize. So first, the question of me is, what you are doing to put the fresh water is a kind of housing experiment all the time?
Mm-hmm. Yes, I mean that's how you would call that.
Just to be sure. Okay, but then how do you think that you would gain more insight if you were doing that where it's directly driven by CO2, or do you think
you mean putting real ice sheets in the model?
Sorry, no,
do you mean like having
letting
sorry,
CO2 an increase of the CO2 with scenarios, for example, and looking at
so increase of CO2 could definitely impact the AMOC, right? Now, if I want to parameterize a meltwater flux, like I did, I have to find a way then to maybe correlate it with CO2 in some way that makes sense, I guess. I mean, here as you said, the idea was really the philosophy of housing experiment, where the only thing that I control is how much time the ice sheet takes to tip and when they occur, right? And you can do that independently of like scenarios and stuff like that, but then interpret it in light of the warming you have in different scenarios, right? For the moment, that's what has been done. But obviously, in the future, if there is, for example, just interactive ice sheets, then there is more or less only one experiment to do and see what occurs, right? Makes sense.
And then I have a last question. But maybe it's you have to go to a slide. One of your last slide when you make this 20 meters change in the sea height, I think. And you say the AMOC is collapsing, but that's because you are looking at SST as a proxy for AMOC, right? Well,
I mean, I would like to answer this question. Actually, I'm not sure. I just know that, from proxies, probably the SST and other stuff, people concluded, let's say, that this is a moment where the AMOC recovered. Now, was it the SST or something else? I have to admit, I'm not sure. It was also probably after the meltwater pulse. I mean, during the deglaciation, basically.
So you would consider an SST as a good proxy for AMOC?
This I wouldn't make statements about that, to be honest. I didn't dive enough into the literature to know which paleo proxies told us that at this time the AMOC was recovering, so I'm not sure.
Okay, thanks.
No problem.
Would like to know, but thanks.
Yeah, me too.
I see no other question. I have an additional one. In the second paper, so in the middle part, somewhere slide 15, 16, and so on, you discussed the rate effects. I didn't fully understand why they happen. Yeah. So on the slide before, you explained nicely how the meltwater from the southern hemisphere can stretch your tidal node diagram. I think slide before, yes.
Yeah.
And then it's a race between that stretch and the actual hosing from the north, right? But then why do you get, is it because the stretch then leaves the state in disequilibrium? So, or is there something additionally going on that we don't see here in this diagram, maybe a vertical shift or what?
No, I guess you would see it, but the point is that because there is this shift of the bifurcation diagram, there are some trajectories that, I mean, even if you go beyond this point, you will not go beyond the tipping point because at this moment the tipping point will be there, right? So you never leave the bistable region in the configurations that are within this this contour basically. But then you observe that the experiments where you actually observe a stabilization, so moments in which the AMOC should have collapsed but did not because of West Antarctica, is this one in blue. And it's just, if you would understand that as bifurcation-induced phenomenon, you would expect that both of them are the same. And you can validate the fact that it is rate-induced because when you decrease the rate, you have actually the match of these two regions. You see?
Yeah, I see. It's not a rate-induced transition, or
no, it's a rate-induced effect.
Just an effect that is because of the delay. Okay.
Yeah, exactly.
I see. Thanks. Cool. More questions? There's still some time. Henry?
Yeah, in the GCM experiments, eventually the AMOC does recover. Is that something that the box models are capable of? Do we have the physics of the recovery in there?
So it depends on the box model. I would say, like, you in Climber X, but it is not, I mean, it's a very big box model, let's say. You have that the AMOC will recover when you stop the forcing. So basically, I mean, that's what you see. I mean, basically the black curve here, if you stop the Greenland forcing, at some point the AMOC will come back to its present state. In box model, it will depend on if the lower saddle node, that is the recovery, is above or below the zero forcing, right? I mean, that depends on where the hysteresis is. But at least in this model, you have the recovery at present state. And in the box model I showed also, actually. Yeah.
Okay, please don't hesitate to ask last questions. Sergio?
I see one. Yeah. Hey, Sergio.
We don't yet hear you. No? That was a mishap.
Maybe.
Sorry, I'm speaking with Jan's microphone now. I was having some issues with my computer. Sorry. So thank you so much for the presentation. I have a question related to the meltwater pulse thing that you commented at the end of the presentation. Have you think about the different scales of the freshwater fluxes that were having in place at that moment?
I mean, obviously you cannot do 20 meters of sea level rise with this meltwater pulse, which would rather bring like 4 meters of sea level rise or something like that. So obviously it's a different situation. I mean, the only motivation here is just that if I look at the experiment, I just look at the timing of what occurred. You see the kind of chain of events that's at least people think occurred at the time.
So you think the is more important the timing rather than the scales of the fluxes respect of the hemisphere that they are coming from?
No, I mean, I wouldn't say that. I would say that if the scales are not agreeing, which it is the case, at least the timing do. And so that could be, at least part of the motivation is okay. I have a 50% hope that it could tell something, basically.
Okay, great. Thank you so much.
Thanks.
Thanks, Sacha. Thanks very much. That was very interesting.
Thank you for having me.
Thanks, everyone, and see you soon.